Now the definite integral can certainly represent area, but you have to be careful because not every definite integral is representative of area, because definite integrals are used for a lot of different applications. But in certain conditions, the definite integral is a great tool for finding the area between a curve and the x-axis. So first of all, the function has to be continuous, and it can't be negative on the closed interval from a to b. If it is, then the area of the region bounded by the graph of f, the x-axis, the vertical lines x equal a and x equal b, can be determined by this formula. Okay, so if you want to find, let's say you want to find the area, let me scroll this out just a little bit. Let's say you want to find the area here that's bounded above, so it's bounded above by this function here, and it's bounded below by the x-axis. It's bounded to the left by x equal 1 and bounded to the right by x equal 2. Whoops, where am I at? There we go. Alright, so it's bounded to the right by x equal 2. So basically what we've got here, try that again. Alright, but basically what we've got here, I'm just not doing a very good job there, but this dark region that's between these four boundaries that I drew here, we can actually calculate that area of that weird shaped object by using a definite integral. The definite integral can be represented as the area from 1 to 2 of x squared dx. Now, right now we're not actually concerned about evaluating. I'm just trying to show you how the area can be represented by this definite integral. One thing I should have mentioned here is notice that as x goes from 1 to 2, notice that the function is continuous and it's not negative. Okay, so that's important. The function is continuous and it's above the x-axis there. All right. Let's say you wanted to find the area bounded by the function square root of x and the x-axis from, say, 1 to 4. Okay, I learned my lesson there and drew it before we started talking about this. So here's the boundary on the left, here's the boundary on the right over here, and then here's the boundary below, and of course the boundary above is just this function. So it's just that function there. Alright, so if we want to find the area of that dark shaped region there, we can actually use a definite integral. Again, the function does not go below the x-axis as x goes from 1 to 4, and the function is continuous as x goes from 1 to 4. So this integral would actually tell me the area. Okay. Now, on one of those examples, you should already know the answer, because up here I gave you a practice problem, I believe. I said integrate from 1 to 2 this function, and I said you should get an answer of 7/3 or 2 1/3. So based on that, since this integral should equal 7/3, then we know that this area in here should equal 7/3. So, and again, I did it using the definition of the integral. But basically, I just want you to understand the relationship between area and a definite integral at this point. Now, I want to talk about a few properties of definite integrals to end this section, and then we'll be ready to get on to the fundamental theorem of calculus. First of all, if f is defined at x equal a, if the function is defined at x equal a, then if you integrate, anytime you integrate a function from a to a, you're always going to get 0. And that makes sense because if you integrate a function x squared, say from 5 to 5, then if you think in terms of area, you're not really given any width. There's no width to the actual area, so basically you're going to get 0. Another formula here is, or another property here is that the integral from a to b f of x dx is actually minus the integral from b to a f of x dx. So if you were to evaluate the integral 0 to pi sine x, and you were to evaluate the integral pi to 0 of sine x, you would find that they're just opposites of one another. So if you reverse the order of integration, all you do is get the opposite sign. So that's an interesting property. Also, if you want to integrate a function from a to b f of x dx, well, you can basically pick any number that's in the domain of the function, let's say c, and then you can break up this integral into two different integrals. You can integrate from the lower limit to c, and then you integrate from the c. I've actually got this backwards. That should be c, and the upper limit should be to b. So switch that around there. Okay, so a to c, and then the second integral c to b, and you can add them together. Now I could show you this with a picture, because basically all you're saying, if you could think of this visually as like if you were integrating this function from 0 to 4, you would get that area. Well, if you broke it up, say you integrated it from 0 to 1, then you would get say an area to the left of this. And then if you integrate it from 1 to 4, you would get the area to the right of this. And then if you add those two together, you get the original area. So that kind of makes it make sense when we talk about area. So if you wanted to integrate the function 2x from 1 to 5, well, you could just pick a number. Now, it turns out the number doesn't have to be a number between 1 and 5, but in most cases that's what we use. If you pick a number between 1 and 5, like 2, then when you integrate this same function from 1 to 2, and then integrate that function again from 2 to 5, well, it turns out that the original integral is equal to the sum of those two integrals. And again, it's kind of like you're breaking up the area into two pieces of area such that when they add together, they give the entire area. There's also a rule, a constant multiple rule for integrals. So if you have an integral of k times f of x, that's equal to k times the integral of f of x dx. So here's an example where I can show you this. Let's say we know this integral is equal to 21. So the integral from 1 to 4, x squared dx is equal to 21. Well, let's say you want to find what's the integral of 5x squared dx from 1 to 4. The limits have to be the same. All right, well, based on this, I can factor the 5 out, and now that I know that this integral is 21, then I know that this integral must equal 5 times 21, which is 105. And then let's see, what else do I have here? Oh, if you integrate the sum of two integrals, definite integrals, it's the same as the sum of the two definite integrals of the two functions. So an example of this would be like if I know that the integral from 1 to 4 of x squared is 21, and I know that the integral of 1 to 4 of square root of x is 14/3, and someone says, well, hey, can you tell me the integral from 1 to 4 of x squared plus square root of x, the sum of those two functions? Well, I know from this property that I can break it up as the sum of the first function, or the first integral, plus the second integral. So now, since I've already given you that the first integral equals 21 and the second integral equals 14/3, I can just add them together to get the result of the sum. And then, of course, you can do 4 and 5 combined here. So let's use the same examples. The integral of x squared dx is 21 from 1 to 4, and from 1 to 4 square root of x dx is 14/3. Then if someone says, well, I want you to integrate 2x squared plus 3 square root of x dx on the same limits 1 to 4, well, then using these properties 4 and 5, you can write the first integral as 2 times the integral of x squared dx, and the second one is 3 times the integral of square root of x dx, and both from 1 to 4. And then you can, since you know what each of these integrals equal, the first one equals 21, so this would just be 2 times 21, and the second one equals 14 thirds, so this is going to just be 3 times 14 thirds, and so you just get 42 plus 14, which is 56. And then I want to end this section on a couple of properties that preserve the equality. If f is integrable and non-negative on the closed interval, then that integral over a to b must be greater than or equal to 0. So in other words, and if you think about it, like right here, if you integrated the square root function from here to say here, all right, so if you integrated from there to there, well, you can see that the square root function is above or is above the x-axis, so certainly it's non-negative. Well, it makes sense that you're going to get a non-negative number because that integral represents area, so that area, it's not going to be negative. Now the second one's a little more complicated. It says if f and g are integrable on the closed interval from a to b, and if f of x is less than or equal to g of x for every value in a to b, then the integral of f of x must be less than or equal to the integral of g of x. Well, if you look here, let's say that this is the g function, and let's say that this is the f function. Okay, so actually what I've got here, and I blew it up for you, this function, this g function, is x squared, and this f function, the f function is square root of x. Well, if you integrated this function over an interval, it would give you the entire area between this function and the x-axis. If you integrate the other function, it's going to give you only the area below the f function, the square root function. So obviously this brown area is certainly less than or equal to the area, the entire area below the top function. So in other words, what I'm trying to say is since this area, this brown area, is less than or equal to the total area under G, then the integral which represents that brown area must be less than or equal to the integral of the gray area. And when I say gray area, I'm talking about the area that goes all the way down to the x-axis. Okay? So in other words, since square root of x is less than or equal to x squared over the interval 0 to 2, then we're guaranteed that this is true, that their integrals will have the same relationship. Okay? And that ends this section, so we'll move on to the fundamental theorem of calculus, I believe, in the next section.